Okay.
Do we get counted if you like can cut off the circulation on half of it that's over here and cost the university less money? Yes. Do you see where I'm going?
Yeah, I mean, sounds reasonable.
I think we should all push for that.
Yeah.
We should all have more money in our pocket.
It'd be nice. Okay, so let's see. Today's the 5th. And last time we were talking about what?
Volume.
Volume, that's right. Okay, so then we more or less covered that idea. Good. So now, the main thing I want you to take away from that is that in the end it was like using integration, but just one more time. In particular, we took those solids of revolution and we cut them into, we made an estimate for their volume by cutting them into cylinders, and then letting the number of cylinders become infinite. All right? So then the very last thing that we talked about last time was average. And just to retread that ground just a little bit, suppose that we have two values, a population, and you can think of this like a population with two members in it. So two members, x1 with value 13, x2 with value 26. Then I could ask you to compute the average. Of course, just like we said last time, you can do that by adding these up and dividing by 2. If you carry out the arithmetic, well, that'd be 39, adding them up, and then half of 39 is 19 and a half. Okay. So that's average. But what I want to make sure that you see is that this is the average in the sense that, note, if we make a new population, with two members. So that is to say, here's a population with two members. Let's make a new population with two members. And let's make them all have the same value. That is to say that these two members have to have the same value, unlike these two, which don't. But if we want this new population to have the same average as that population, then what needs to be the value that all of the members of the new population have? Yeah, 19 and a half, right? All with the same value, and we want the average of the new population to be 19 and a half, which is to say the same as that one. Then this new population has to be 19 and a half is the first one, and 19 and a half is the second one. So that's what is meant by average. So, you know, if we had a million members, we could compute the average by adding up all million of them, dividing by a million. That would give us the average. And then we could make a new population that still had a million members in it, but they all had the same value. And the new population would have the same average as the old one. That's what average means in this case. 2. If we have x1, x2, x3, up to xn. Now n could be a real big number, like millions and billions and things like that. So we've got a population of n elements. Then we went over it last time, the way to compute the average. Is by the following formula. You do 1 over n multiplied by the summation from I is 1 to n of xi. So that just means add them all up and divide by n. So that's average. Now, notably, this formula works for finite n, even if n is really big, so like millions of x's, it'll work. But it won't work for infinitely many x's because, for example, this 1 over n issue, 1 over infinite would be 0. Okay, so then that couldn't work. All right. So this is what we want to do. So we could say let f of x be a function defined on the closed and bounded interval a to b. And just as a technical matter, it needs to be the case that a is less than b. Because strictly speaking, the closed and bounded interval 3 to 3 is an interval, and it's closed and bounded, but it only contains 1 point. Okay, so then we're not interested in that sort of trivial case. So we've got a function a to b. And so here's the thing. For every height that you see, there's a y value. So how many y values does this function have? Infinitely many, right? Because like, well, because there's an intersection, that's a particular y value. Now if I move up a little bit, that's a y value, that's a y value, that's a y value, that's a y value. All of these are y values. So how many different y values are there? Well, there's infinitely many. And you know, just generally speaking, how many red points are there? Infinitely many. So there's infinitely many points. And therefore, if we want to compute some kind of average, then we can't use this. Right, in the end, because there'd be infinitely many values to deal with. And this formula is only going to work for finitely many. All right? Nevertheless, we want to somehow compute an average. And here's the thing, is that, so here's a population with 2 members that's not constant, because it's not a constant population, because here's something that has a value 13, and here's something that has value 26. Here's another population with 2 members, but its value is constant. Notice that all of them are 19.5. And what I want you to see is that the averages of these 2 populations are the same. All right? So here, this red function, is it a constant function? It's not a constant function. It's not a constant function. You can see that it's not because it's going up and down. So its output changes depending on its input. What we want, to make / find a constant function that somehow represents the average of f of x on the interval from a to b. Now, the way that we'll know that we have it right is as follows. So in the first place, if we were to plot a constant function on the interval a to b, how does it look? How do constant functions plot? Horizontal lines, right? So like, for example, the constant function h of x equal to 19.5, well, that'd be a horizontal line at height 19.5. Okay, so what I'm telling you is that we want to find a constant function, which is to say we want some kind of height, some kind of level. So like there's a constant function, I just mean this graph height. There's a constant function, there's a constant function. We want to make / find a constant function that represents the average on a to b. We will know we have it when the area of this one so that is to say that area there is equal to the area of so we have to somehow pick out the perfect height. And I'm saying that, you know, maybe that's the perfect height. Okay, so to be clear, I'll give you, you know, sort of 3 different options here. Okay. So here's 3 copies of that f function. Okay, so I'm going to put one of these green functions, one of these constant functions on offer. So like here's an example, constant function. Now I have a question for you. Consider the area under the red curve from A to B and the area under the green curve from A to B. Are they the same? If not, which area is the greater in this one? The red, the area under the red curve from A to B appears to me to be more than the area under the green curve from A to B. Because you can see that, you know, there's a little bit where the green area is picking up the area that's not covered by the red, but this seems to be a lot more. Okay, so what I'm telling you is that that appears to me to be too low. Too low. Similarly, how about maybe like this one? So now, comparing the area under the red versus the area under the green. Which one appears to have more area? It appears to me that the green does. Because even though the red accumulates a little bit more area than the green right there, that bit appears to me to say that, you know, that right there would be too high. So what I'm telling you is that this is like a Goldilocks issue, right? My porridge is too cold. My porridge is too hot. Somewhere there's got to be just right. There's got to be some level where this constant horizontal function has exactly the same area as the red one. So, you know, this isn't an art class or anything, just eyeballing it. Okay, I'm not going to get out a ruler. Okay, so that appears to me to be about right. Because the amount that it's over there appears to me to more or less exactly offset the amount that it's under. So can you see that, this one is just right. So this is just right. And that is what we're looking for. So does everybody understand what it is that we're looking for? We haven't talked about how to get it. I'm just describing what it is that we want. The idea is that, well, here's the formula for average for finitely many points. In the case of a function, we have infinitely many points. The idea that we want to make happen is that we want to find this this level, this constant function that has the same integral, the same area. Good. So here we go. So this is the definition of the average or mean value of f of x on a to b. And again with a less than b, which gets rid of the trivial intervals. Okay, so the first item, just as to give you just a little bit of intuition, consider, for example, the function h of x is equal to some constant like 4 on a to b. Well, if you were to plot it, it would look like, you know, like this. And this would be, you know, at level 4. Well, what's its average value? 4, right? Because that's its only value. So it's, well, there you have it. So this has average value 4. Okay. So what I'm telling you is that the notion of average value for a constant function is a meaningful thing. If if we had a different function that was like this, h of x is equal to, say, 4 if x, well, I'll say it like this, if x is in a to a plus b over 2. That is to say, it's in the left half of the interval. And if it's equal to something like 10, if x is in the right half. So what I'm telling you is that this function looks like this. So we take the interval, okay, and then we split it exactly in half. Because after all, what is the midpoint of interval AB? A plus b over 2, right? So this function that we're looking at, it spends half of its time being 4, and it spends half of its time being 10. So notably, exactly half of its time it spends being 4, and exactly half of its time it spends being 10. So what's its average value? 7, right? Because it's just got two different values, 4 and 10, and because the same amount of time is spent being 4 as is spent being 10, that means that they should be weighted equally. So, because each interval has the same size, we'll weight each y value equally. So then, that just means 4 plus 10 over 2, which is, of course, 14 over 2, which is 7. All right. So now we need to get to the general case. What if we have f of x on the interval a to b? And it is not constant. So now, while you're pondering that, can we agree that I split this one into 2 equal pieces, and it was constant on the first piece and constant on the second piece. And because it only took on those 2 constant values, and because the time was exactly half that and half that, we just average them together like that. Can you agree that if I had split the interval into thirds and there were 3 different y values, then we could do the same thing and divide by 3, add them up and divide by 3? And if instead of splitting it equally into 3 pieces, if I split it into 4 pieces, then we could add up all the y values and divide by 4. Now, this is not a piecewise, so this is like a piecewise constant function. It's constant in that piece, it's constant in that piece. This is not a piecewise constant function, it's kind of smoothly varies. So what are we going to do? Surely there's some kind of calculus coming up, yeah? So, well, this isn't a piecewise constant function. This one, piecewise constant functions that kind of look like staircases. They don't need to always go up or always down. You know, they can go up, down, blah, blah, blah. But they need to look like kind of like staircases. What if we do that to this one? What if we approximate this one as a piecewise constant function? What if we say, okay, let's approximate f of x on a to b with a piecewise constant function. Specifically, we're going to do the same. It's going to start to look really familiar in just moments here. What if we say, okay, here's a copy of our f. And suppose we cut that interval into 4 equal pieces. Four only so I can draw a more or less comprehensible picture. But understand that that means n. So now, in each strip, we'll sample. So say like I sample right there, and that gives me that rectangle right there. And maybe I sample here. That gives me that rectangle there. Sample there, like so. Like so. All right, so now what I want you to see is that taking that red function, cutting its domain, a to b, into 4 pieces, and then choosing one sample for each point, now we've made a new piecewise constant function. So now I'm going to remove y as f of x, only to make the picture more comprehensible, easier to see. Okay, so now we've got this green function. Do you see that it's piecewise constant? It's like a staircase. Furthermore, remember that the way that we cut this up is we cut it up into 4 equal size pieces. In particular, because they have equal size, that means that they all have the same size. So what's that total length right there from A to B? Well, that'd be B minus A, right? Like if I was asking what would be the total length from 12 to 20? Well, it'd be 8, right? Because it'd be 20 minus 12. So this total length is B minus A. And because we've cut this into 4 pieces, that means that each one of these pieces has size delta x equal to B minus A, and then what? Divide by 4. Because we're saying that each one of them is an equal piece of B minus A, and we divided it into 4 pieces. All right. So now I have a question. Keeping with our previous notation for the way that we do this cutting up and sampling thingy, we referred to this sample point as C1, this sample point as C2, this sample point is C3, this one is C4. So what is the height of that rectangle, which of course is the same as that rectangle? I know I didn't draw it perfect, but imagine. F of C4, right? So this one, that height right there that I'm pointing to in both places, is f of C4. So the y values use in this drawing are, well, the rightmost y value is f of c4. What's that one? Right, and f of c2 and f of c1. Okay, so they are f of c1, f of c2, f of c3, and f of c4. So what I'm telling you is that because this is now, the green function is an estimate of the red function, and because the green function has finitely many y values spread out over equal size pieces, we can construct an average for the green function by just averaging up all those y values. So that'd be f of c1 plus f of c2 plus f of c3 plus f of c4, like so, over 4. Now, we talked about this last time, and I even wrote down this formula because we talked about it last time. So now I'm just going to write down the corresponding thing here for this one. This would be a fourth multiplied by the sum from I is 1 to n of f of, not n, 4, because we're doing the specific case of 4. F of ci. Okay. Now, but I want you to keep in mind that this summation, all that is that's a nice short way to write the numerator, right? Just the adding up all of the f of c thingies. So that's what that is. And in particular, what this is saying something that is more or less 1/4 multiplied by f of c1 plus ... all the way to f of c4. So that's what that's saying. Now, that's product and that's sum, which means that we can distribute the 1/4 in, right, to give a 1/4 to that one, and to the next one, and to the next one, and to the next one, because multiplication distributes over addition. So that's what I'll do first, is I'll say, okay, this is the sum from I is 1 to 4 of 1/4 multiplied by f of ci. So what I did is I changed it so that it looks like this. 1/4 times f of c1 plus ... plus 1/4 of f of c4. So I distributed the 1/4 in. And now I'm going to commute the order of that product. And all of this has been really pretty boring, but now I'm going to start pulling rabbits out of the hat. All right. So all I did is I commuted the product, the order of that product. That's a perfectly legitimate thing to have done. Now here's the thing. I'm going to multiply by 1. So I put that red 1 there. It's a fine thing to multiply by 1, but I'm going to pull a rabbit out of the hat by multiplying by something that's extremely convenient. So besides the literal 1 there, there's other things that are equal to 1. An example of something that's equal to 1 would be something like 8/8. 8/8 is equal to 1. -10 divided by -10, that's equal to 1. You can think of a million different ways to write 1. So what I'm going to do is, for reasons that at least at first won't be entirely clear, I'm going to multiply by something that's equal to 1, but it will be very convenient. So that's all that stuff. And here comes my 1. Now, b minus a is just some number. I know that it's a positive number because at the beginning I said that b was more than a. So I'm multiplying by b minus a and dividing by b minus a. So that red bit, that's 1. So now I'm going to split it. I equal 1 to 4. F of ci, a fourth. Now I'm going to split it like this. I'm going to say that this is multiplied by b minus a, multiplied by 1 over b minus a. That's just another way to write that fraction. So now I'm going to put this b minus a on top of the 4. And now, here's the thing, is that you saw from this step to this step, I distributed the 1/4 into the sum. Well, you can do that with constant multipliers. 1/4 is a constant and it's a multiplier, so I distributed it in. Now, this 1 over b minus a is also a constant multiplier, so I'm going to now distribute it out. I'm going to factor it out. All right? So now it looks like 1 over b minus a multiplied by the sum from I is 1 to 4 of f of ci times b minus a over 4. And now we have one more. One last thing. As it happens, as it turns out, we already have a name for b minus a over 4. What was it? Delta x, right? So, delta x just being the size of the equal size pieces that we cut the interval into. Now, what I'm telling you is that this is a formula for an approximation. So this is an estimate of the average value of f of x on a to b using 4 strips or rectangles or whatever you want to call them. So that's what that is. Now, for every engineering problem, there's some number of rectangles where it's enough. So your engineering problem, 4 might be enough. But if not, then maybe 44. And if not that, then maybe 44 million. Okay? But can you agree that in this formula, the only thing that represents the number of rectangles is that 4 right there? So in particular, if we wanted to use n rectangles, I just copy down this formula and write down an n. Okay. that would be 1 over b minus a multiplied by the sum from I is 1 to n of f of ci delta x. Okay, that's where you cut into n equal pieces, even if n is like a billion. Okay, and then as I was saying, for every engineering problem, there's some n where that's good enough, right? Because eventually, the size of the pieces that we're talking about, you know, they get to like the size of atoms, right? So there's got to be some n where in any given engineering problem where that's enough. But you know, this is calculus, where we basically go with the idea that's saying, no, let's just think what it would mean if the number of rectangles actually did become infinite. Okay. So therefore, letting n go to infinity. So we have exactly that formula there. 1 over b minus a times the sum from I is 1 to n f of ci delta x. And then what is the math notation that signifies letting n go to infinity? Limit, right? So then now we have the limit as n goes to infinity of this thing. And well, remember that 1 over b minus a is just a constant. It's just a constant multiplier, and here's the thing, is that the limit is homogeneous, which means that that constant multiplier can be factored in and out. So we can just factor that 1 over b minus a out, just like you can factor out constants out of derivatives, antiderivatives, and integrals. So that means that conceptually we can just ignore this for the moment and just ask, and just look and say, oh yes, I see. Now we're going to make the centuries-old calculus joke, where we take an expression involving Greek symbols, compute a limit, and then all the Greek symbols become their corresponding Latin symbols. Right? Ha ha! Yet again. So the answer will be 1 over b minus a multiplied by the integral from a to b of f of x dx. Okay, so now, this is a formula that you're now expected to memorize. This is the average value of f of x on the interval a to b. So that's what it is. In particular, it's telling you more or less that if you have if you have a population with infinitely many members, and their values are given by this function, then the way to compute the average value of the population is with this integral. Now, if we compare this to this other formula that we wrote on the previous page, I'm just copying it so that we can look at it. So let's just look at them and compare. So this formula, the formula for computing average when you have finitely many things, it's saying add them all up, divide by the size of the population. Add them up, divide by the size of the population. And I think that's entirely natural, right? So when I asked, if I gave you two numbers and asked you to compute average, you said, add them up, divide by 2. What I'm telling you is that's exactly what this formula is saying. This formula is saying, add it all up, divide by the size. Add it all up, divide by the size. So these formulas are really saying exactly the same thing. It's just that this one is when you have finitely many things, and this one is what you do when you have infinitely many things. So this is the average value. Of n values. Okay. And hopefully not to overstress the point too hard. But, you know, I'll risk it. In picture form, it's saying the following. Is that if we have a function on interval a to b, so if you're taking the time to draw stuff, I would like for you to take the moment to try and draw that rectangle, the green one that we drew, this one, for the function. So you want the rectangle that gives has the same area as the area under this curve. And then when I'm trying to do it, I always turn the page this way. So this is just eyeballing it now. I'm not getting out a ruler or anything. That appears to me to be the height, that the area under that horizontal line is the same as the area under the red curve. So those two areas are the same. And what the result on the previous page is saying is that the height of that line is what? It is that. That's the height of that line. That one right there. So now, to be clear, and to make sure that to hopefully have understanding. So B and A, those are just numbers. So can we agree that 1 over B minus A, that's just some number? And furthermore, can we agree, what kind of thing does the integral output? Does it like output like a cat or like a number, right? It outputs numbers. So that's a number. That's a number, and the product of those two things is a number. And what I'm telling you is that that number right there is that height. That's what that is. And this particular rectangle is, for those of you that just like to know the name of these kinds of things, that green rectangle is called the mean rectangle. That's its name. Now, that being said, we won't really be referring, I won't be using the language mean rectangle at all, but from here on. But if you get the idea that you want to take a bunch more calculus courses, it could happen, then it'll come up. Okay. So any question before we do an exercise? All right. So here's an example of an just abstract exercise. I'll do it like this. Find the average value of h of t equal to 3t squared minus 4t plus 5 on about 3 to 8. Okay, so then there's a lot of things that are like hinting at that we should that we should use the formula, this formula right here. One of them is that we just finished deriving it, but you know, there'll come a time when it's a little bit further on. In the end, the key idea is that it's average value of a function on an interval. So you just have to identify that concept with that formula. All right. So then, now the formula we wrote down with variable x, and here we're using variable t. But there's nothing special about that. That's not relevant. We just changed the variable name from x to t. So in the end, is there any question that this is what we have to evaluate? Okay. So then on this specific exercise, what are a and b? 3 and 8. So this should be 1 over 8 minus 3 multiply integral 3 to 8. Okay, and now I'm going to write something that is incorrect. But I've been saying it's incorrect all semester, but you know, I keep asking y'all to submit stuff, and I keep grading stuff, and it keeps getting submitted. So, what I've written is not correct. To a certain extent, what I've written is sort of like nonsense, in the same kind of way that if you were speaking a foreign language and you were attempting to say a sentence, but you left a word out, then the people trying to listen to you would have difficulty understanding what you could possibly mean, since you left a word out. So what's not right about this? The dt is missing. Okay. So I'll write the dt. Okay. Nevertheless, so it's more nearly right. It's more nearly right, but still not right.
I got like a bunch of things that say it's parentheses,
Yeah.
but on like the Lexis and stuff, there's no parentheses when they're like, you know, in the question form.
Mm-hmm.
When it says like anti-differentiated, like there's no parentheses in the question.
Okay. Let's talk about that for a moment. Here's what am I trying to say? As an aside, let's look at this. How about x plus y, and then suppose I put a 5 here. Okay. So now, what's the meaning of that 5 being juxtaposed with the y? What does that mean when you do that? It means, yeah, in the end, it means writing the y and the 5 side by side. That means multiply them. Okay. Now, you know, one of the things that I hear from the grapevine is, oh, Dr. McCary, he's the one that always writes the dot. even though we know we don't have to write the dot. For some reason I can't understand, he writes it. Okay, so no dispute. That's a that's a valid characterization of me. Fine. So here I'll write this again: x plus y, and this is probably more nearly how I would write it. Okay. Now I have a question for you concerning this expression. Which elements, if any, is the 5 multiplying? The y. Is it multiplying the x? Why not? Because why?
Did you not put the parentheses?
Okay, right. Because in the end, the order of operations says that multiplication binds more strongly, has a higher precedence than addition, which means that this 5 is only multiplying the y. Suppose that we wanted it to be the case, that the 5 was in fact multiplying the x and also the y. Then what would we need to do? Well, we'd have to put parentheses. So now, the order of operations, parentheses being first, means that that summation occurs before that multiplication. Okay, so now the 5 is in fact multiplying the x and the y. So now, here's the thing, is that this is one of the reasons why I always write the multiplication. This is one of the reasons right here. Because that dt is an object. Specifically, it's called a differential, or a differential form. So I have a question. Of the three terms here, 3t squared, negative 4t, and 5, which of those terms is the dt multiplying, if any? The 5. Is it multiplying the 3t squared? It is not. Is it multiplying the negative 4t? It is not. So here's the thing, is that the kind of thing that dt is, it's called a differential, or a differential form, and the only kinds of things that it makes sense to integrate are differential forms. So the way this reads is is more or less saying something like integrate this function. And to a mathematician, that doesn't make any sense. That'd be like you saying, like, eat this block of wood. Well, we don't eat blocks of wood. It doesn't work that way. We integrate differential forms. So, in fact, we want the dt to multiply all of these things. So how do we make it right? Well, with parentheses. Now, to your comment, which is a valid one, I offer the following reply. This that's just an oops. X squared dx, this is okay. It's permissible to write that. You can write this. That's okay. If you felt really, I don't know what you might be feeling, but you could do this too. This would be okay. That'd be okay too. Now, here's the thing. This is okay. That's okay. But this one is not okay. Now, why is that one not okay? Yeah, because in the end, the statement, this statement right here, function plus differential form, doesn't make any sense. It's like nonsense. The only thing you could possibly mean is this one. But leaving the parentheses off is just like leaving words off of a sentence. Yeah?
So this is like if the growth,
Mm-hmm.
do we assume that the dx go to the whole?
I'm not sure I understand what you mean.
Like we're just assuming that the dx gonna always apply to the whole equation, not just any single one.
In this kind of context, I think I understand what you mean, but let me say this: in other classes, if you were to go on, then it would make sense to write something like this: the integral over some object. Ignore what this means, but this is taking the place of a to b. You could write something that looks like this, something like x squared y dy plus, say, 4x dx. Like you could do this, where now there's two different differentials involved. So that one and that one. So in this case, this would be a differential, but the form would be dy, and this would be a different differential, but with form dx. And it's all going to be done over some thing we're calling omega. So what I'm telling you is that this statement right here, x squared and then plus 8 dx, is it doesn't make any sense. And I can't really explain to you the exact nature in which it doesn't make any sense, but I promise you that it doesn't. And the way that you get around it in the end is parentheses. Okay, good. So now that we're past that just technical issue, yeah?
Okay, my comment was that on the homework,
Yeah.
there are no parentheses when
Okay.
the question is stated.
Okay.
So you can see how, like, so why is it permissible to, when stating the question, leave off parentheses and then?
I'm not really, you know what? I'll say it this way. I think I have strong doubts that I left off any parentheses that it didn't make sense to leave off. So what I'm saying is that it's perfectly okay to write an antiderivative or an integral like this in the end, because there's just a single term, x squared.
Yeah.
You can omit the parentheses. Both of these are permissible. But because this expression right here consists of two terms, it's not permissible to leave out the parentheses. So it sounds like what you're saying is that maybe I posted a homework exercise where it's not there.
I guess, okay, if every term is a multiplication term, is that different?
No, okay, now I understand. Now I understand. You might be asking about this, and this is okay too. So something like, say, like x squared times the logarithm of x dx.
Yeah, or if Lx was anything else, if it was also a multiplication.
It'd be fine.
Okay.
In the end, the distinction is that when you have a plus b, anything that looks like that, these things, the things separated by pluses and minuses, are called terms. Things that are separated by multiplies and divides, these are called factors. So the thing is that if everything is factors and there's just a single term, then parentheses are not necessary. In the end, the reason is because the way that the differential is added is added as a factor. So because there's two terms here, this has to be a factor of each term. And because multiplication has higher precedence than addition, you have to parenthesize it.
Okay.
It will always be safe to parenthesize it. You can always write the S, parentheses, whatever you got in there, and then D, whatever. It's always fine. Okay, so here we go. Good. Let's just zoom past this part because now this is boring. So 1 over 8 minus 3, that's 5. We can use the fundamental theorem. That'd be what? T cubed minus 2t squared plus 5t, and then evaluated from 3 to 8. Any question about that? Then, who knows? I don't even know. How do we do this? So this would be a fifth, and then that's calculator work if I ever saw it. Let me do that real quick. 8 cubed minus 2 times 8 squared plus 5 times 8. 424. Subtract. 24. And that's nice. 400 over 5 is 80. Okay, so in a sense, the numerical value is 80. But then I want to make it clear, what is the meaning of that number? What's the meaning of it? Well, if you were to plot, or just a, so here is just the answer. All the rest of that was just, that's just an aside. So that's the answer. But as a continuation of aside business, the sketch of, say, W is equal to h of t. If we were to sketch that, how would the plot appear? What would that look like if you plotted it? Parabola. Parabola that opens up. Now, I'm just going to draw a quick freehand sketch of a parabola that opens up. I make no warranty as to having the intercepts or anything like that right. Okay, but at any rate, we've got 3 and 8. 3 and 8 there. And some kind of parabola. I don't know where the vertex is. I'll just, you know, pretend that it's about right there. All right. So I drew a parabola. What does 80 have to do with this picture? Height of what? Right. Is consider. Can you see this area that would be the integral of this red function? The question is what rectangle would have that same area? And just eyeballing it, again, you want to choose the rectangle where the overshoot of the red is offset by the undershoot of the red. So something like, you know, maybe like that-ish, because that is about equal to that. You know, I'm not trying to be an artist here. So what I'm telling you is that, what is that value right there? How high is that? 80. And that rectangle is called the mean rectangle.
So that's the just the height, not the area.
It's not the area, but the whole area, because this is 5, and that's 80, the whole area is 400. And what I'm telling you is that the area under the red is 400, and the area under the green is also 400. They both have area 400. So, so what I'm telling you is that this area is equal to this area. Is equal to 400. That's what this computation is saying. Good. Any question about it? All right. What time is it? Doing good. This is okay? All right. So fine. Essentially, all the questions are like this. Somehow you just have to use this formula. Okay, good. Mostly the point of that is just, the point of going through that exercise is just that this half of calculus is sort of like, let's really explore this calculus idea where we take something and break it into pieces and then let the number of pieces become infinite. So that's just yet another way to explore that idea. All right, so now we're in section 8.3. And it's titled something like continuous money flow. All right. So what this is that you know, one of the things that you have to have taken before you got here, you know, like in some kind of algebra class or something, is that you needed to take something called interest and compound interest. Okay, so you've got to know what simple interest is and compound interest. And the state of Texas ensures me that you're all experts at that. But you know, for my own sake, I'll review I'll review that a little bit. So here's the idea: is that in the first place we have this idea called simple interest. Interest. So there's almost no financial institution or business institution deals with interest in this way. So this is like not realistic, and we're not going to talk about it besides this little block of paper right here. Okay, so that being said, this might be something kind of deal that you might make with like maybe your like relative or something. You might say like, okay, uncle or whoever, I'd like to borrow some money, and they say, yeah, okay, and you know maybe it's like you know $5,000. Can I borrow $5,000? And then the relative says, yeah, sure, but as long as you are holding my money, I want you to send me $10 every year. You know, just mainly so I know that you remember that we've got a deal and you got to pay me back. Okay, so you just write your relative a check for $10 every year, but the amount that you owe them is not going up, right? So this check that you send to your relative every year, that's an interest, and it's called a simple interest. It's called a simple interest because you know, y'all agreed on $10 a year. But that doesn't get added into your current account balance, right? You don't owe them first $5,000 and then $5,010 and then $5,020, not like that. Okay. So simple interest is more or less the idea is that you have a principal amount, and then at discrete intervals of time, more or less, according to the principal amount, according to what you agreed, is that you send off a check in the mail. Okay. There's nothing more complicated to say about it than that. Now, the question is that so this sending the check in the mail, that is representative of the interest. Now, what if instead of this periodic interest just being handled as a check in the mail, what if that wraps back around onto the current account balance and your balance changes as a result? This is the way it works in real life. The way it works in real life is that you borrow P at the beginning, and then that is your account balance. And then periodically, according to a contract, usually with a bank or whoever, a lender, they say that, oh, well, now you owe us some more money. an interest payment, and we're going to update your account balance like so. So your account balance is changing. The only difference in the picture is that this arrow has now come back around. So it's not a free arrow, it comes back around. So the way this works in real life is, well, all of you are students, and I think it likely that you took out student loans because, well, let's have a frank discussion about what interest is in the first place. Because it's very important for you to make it out of university knowing at least what that is. So here's the thing, is that UTD, they want their money now, okay? They don't want their money in a year. They want their money now. So if you're going to take a course now, then you need to pay now. So that's the way they do business. But here's the thing, unless you're independently wealthy, you don't have that money now. But banks do, right? So more or less you go up to the bank and say, hey bank, it appears to me that you have like mountains of cash. And I'd really like to be in control of some of that cash right now because I want to give it to someone else. And they say, okay, I'm willing to agree to that. But here's the thing, if I give you that cash, then I, the bank, am no longer in control of it, and you're in control of it. And as far as I can tell, that's worth some money. And then you both agree. You say, yeah, it is, because if you don't give me the money now, then I can't do what I want now. So evidently it is worth money. The amount of money that y'all agree it's worth, that's interest. What it is it's an agreed upon scale for how much money it's worth it for the bank to give up control of a resource and give control of that resource to you. That's all that it is. The longer you're in control of the resource, the more money you're going to end up paying for it. The higher the risk it is that they estimate to give you control of the resource, the higher the interest rate you're going to get. So in the end, all that interest is it's just an agreed upon payment for the transfer of control of a resource for a certain amount of time. That's what interest actually is. Now that being the case, there are two models that you learn about in college algebra. So here they are. One of them is called the discrete compound interest. So this one that we're going to write down is actually starting to get kind of realistic about the way money actually works. There are several parameters. There is the principal. It is denoted by symbol P, and it is, you can think of it like the account balance. At time 0. So if you're taking a loan, that's the value. If you're lending, that's the value. Okay. Then you have the periodic interest rate. Denoted by R. Just a couple of notes is that, something like 8%, the way that you write that down with R, that means that R is 0.08 because R needs to be encoded as a decimal. And furthermore, the period is almost always a year. In that case, usually it's called the annual interest rate. Okay, then we have the number of compoundings per period. This is denoted by N. So what that means is that when you go to a bank and you ask for a loan, or you open a savings account or what have you, they quote for you some interest rate. But that interest rate has period 1 year. And the actual compoundings, that is to say, when your account balance changes, doesn't happen every year. Rather, it happens usually every month. So in this case, if that were the case, if the period was a year and we wanted it to compound every month, that would mean that n is 12. If we wanted it to compound quarterly, then n would be 4. If we wanted it to compound weekly, then n would be 52, right? It just goes on and on. So like monthly, so what I mean is that if period is 1 year, and compounding is monthly, that would, those two things would mean n is 12. And then you've just got to think your way through, other scenarios. But I try not to, be too adventurous, because I'm not really sure what the point of that is. I've seen questions, that like they'll say, things like, well, suppose that the period is 2 years and the compounding is every fortnight. You gotta look up what a fortnight is. No, I'm not going to worry about that too much. PRN, and then the number of periods. This is T. So like, if it's annual interest rate, and then we're talking about 20 years, then T is 20. Finally, we have the account balance. At time little t, and this is given by A. So there are 1, 2, 3, 4, 5 parameters in that model. And the model is given by this. A is equal to P multiply 1 plus R over N to exponent N multiply T. So that's a formula, a model that you're expected to know before you got here. So to give you an exercise and the general idea, I'll just give another remark. The main way that we're going to use this is as follows. So like, we have time 0, and we have time, which I'll write as capital T, which I just mean the end. So here's the thing, is that, you've heard the phrase the time value of money or something like that. Here's the thing, is that money, the value of money changes as time goes on. The reason why it changes in the end is because there's such a thing as an interest rate, which means that who has control of it. So here's the thing, is that if you have an amount of money right here, and you're willing to agree to someone else having control of it for this whole period, and then they give control of it back to you right there at time big T, then when you get control of the resource back at that time, it'll be worth more money. So like if you put 5,000 here, and this is a span of a few years at a reasonable interest rate, well, at the end of that time, it might be something like 7,000. Okay, so then these two different positions in time, they're referred to as the present value and the future value. Okay, so that being the case, here's an exercise. I'm sorry? Right. But we're not going to use tables. It depends on how far we get into how far we get. You know, because on occasion we've when I've done this class, we've done things like what are they called? Annuities. Yeah, we get to it, and then you know we go through all the annuity formulas, make big old nice tables, but we're not there yet. We have other things to do before we get there. But here's an exercise. I could say, what is the future value? What is the future value of, say, 2,000, and that is to say now, of 2,000 given annual interest rate of, say, I don't know, 8% compounded monthly. After ten years. So now to put this in sort of plain language, it's saying, well, what if you had $2,000 right now and you were willing to give it to the bank right now and say, bank, you can be in control of it for 8 years. And they say, all right, if you'll agree to that, then we'll agree to 8% compounded monthly. And there really are actual financial instruments that do exactly this. They're called CDs, certificates of deposit. So this is a completely realistic thing. The question is, when the contract is over and the bank gives you the money back, how much money are you going to have? How much are you going to receive? Okay? So this is the model that we have to have. So in particular, what is so I see a number 2,000. In the model, what parameter is that? Which one? It's P. It's the principal. It's the amount of money right now. So given P is 2,000, do we know R? 0.08. Yes. So R is 0.08. Do we know N? It's 12. How do we know it's 12? Because it says monthly. And T is 10. So given those four, find what? Find A. Okay. Well, then the answer is, well, you just plug all this stuff in. 1 plus 0.08 over 12 to exponent 12 multiplied by 10. So that's just some calculator thing there. Oops. I flubbed something. Can you see what I missed? The 2,000, right? Okay. Well, okay, let's imagine that, you know, it was a quiz, you know, and I was in a rush, and I was, you know, all, you know, worried. Okay, so I'm going to type into the calculator everything but that 2,000. So 1 plus 0.08 divide by 12 raised to 12 times 10. So this is everything but the 2,000 there. So suppose I write that down, and I write it down. It's 2.2196. So in the first place, this is wrong. Okay, in the sense that it's not right. Okay, but I mean it's like not exactly the correct numerical answer. But I claim that, in fact, that this is wrong in such a way that it's like to the about to the point to where it's unforgivably wrong, because an answer like this, I claim, is nonsense because of the way the problem is stated. Why is this answer of a little bit more than 2 nonsense? Right. I mean, what should your expectation be about the answer to this question? It's got to be more than 2,000, right? Because what you're saying is that bank, here, look, you be in control of $2,000, you know, and you know, we're not going to worry about markets crashing or anything like that. You're in control of $2,000, okay? And they give you a positive interest rate. Well, you've got to get more than 2,000 back. So can you see that this kind of response is like is nonsense in the sense that it's not more than 2,000? All right. So then, if I fix it, so fixing that, my calculator now says something like 4439.28, rounded to the nearest cent. Okay. Now, does that one pass the reasonableness test? Yeah, at least it's more than 2,000, right? So let me double check here. 1 plus blah, 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 blah. Looks good. Okay, so that's nice. This is saying that under these circumstances, you can about double your money. Of course, you have to understand that you gave up complete control of that $2,000 for 10 years. Whatever. So now here's another idea, a thought experiment. This is the bank. Of Math 1326. So, we only have one contract available in the Bank of Math 1326, is that you're allowed to make deposits, but you're only allowed to make deposits of $1. That's it. Sorry, we don't accept any other deposit amounts. So that's saying that P is 1. Deposit is $1. Also, we have very good interest rates. In fact, our interest rate is 100%. So what parameter is that talking about? It's R, right? So what's the value of R? 1. And here's the other thing, is that we only offer contracts of 1 year. That's it. We don't allow for any lesser or any greater contract length. No. T is 1, right? So this is the only thing that this is the only contract that the Bank of Math 1326 will agree to. However, here's the thing, is that you can use however many compoundings you want. So you can say, well, I'd like for you to just compound it once a year. That's fine. We'll do that. If you want us to compound it twice, okay, twice. If you want us to do it monthly, fine. That'd be fine too. So here's the thing. If we take this formula, the one that's on the previous page, this one, and we substitute in P is 1, R is 1, and T is 1, then we have the following. A is 1 multiplied by 1 plus 1 over n multiplied by n times 1, and then simplifying that a little bit, getting rid of all of the extraneous multiplies by 1, we have this formula. 1 plus 1 over n to n. And what that's telling you is that at the end of the contract, that should be your account balance. Now, let's think about this for a moment. If there's exactly one compounding, the way that I'll, being I guess the proprietor of the Bank of Math 1326, if you say, I just want you to do it once, then okay, I'll hold your dollar for a year. At the end of the year, I'll say, hey, look, I've held their dollar for a year. Well, the contract says 100%, so then look, I put one more dollar in. Your account balance is $2. I close it out and hand it back. Right? So that's what it's saying. So that means that if n is 1, your account balance at the end of the contract should be 2. Let's plug that into the calculator and make sure that that's right. So that's 1 plus 1 over 1 raised to exponent 1. 2. All right, good. So what if we do it twice? So that is to say, okay, I hold your dollar, and then after 6 months, I say, hey, look, I've been holding their dollar for 6 months, and they said they wanted me to compound it twice. So I'm halfway through, so here's a compounding. But I'm not going to compound it at 100%, because it's only been half the time, right? So then I'm going to compound it, but only 50%. So what's 50% of a dollar? 50 cents. So I add the 50 cents in, and now your account balance is $1.50. And it sits at $1.50 for a further 6 months. And at the end of those 6 months, I say, hey, look, it's time to do another compounding. But not at 100%, because they asked me to do it twice. I only need to compound at 50%. Well, what's 50% of $1.50? 75 cents. I add that in. The new account balance is $2.25. I close it out and hand back $2.25. So does everybody understand the process? Let's plug it into the calculator and see if the calculator agrees. So now it's n is 2. So that's 1 plus 1 over 2 raised to exponent 2. And if I didn't fast talk us all into confusion, it should say 2.25. All right, 2.25. What I want you to observe is that increasing the number of compoundings increased the final account balance. All right, what if, again, remember that the rules are that the Bank of Math 1326 requires P is 1, R is 1, and T is 1, but I leave the choice of n to you. Sorry, I got to put some lead in here. Sorry? Increasing n causes a to increase, meaning that if you compound more, then the final account balance goes up. So what I'm telling you is that all of the things being equal, it seems like you should prefer more compoundings. All right. So what if we go to like a more usual contract and say, monthly, n is 12. That means that every month, instead of compounding it at 100%, I compound it 100 over 12%, whatever that turns out to be. So like this, 100 over 12. So every month you get compounded 8.3%, like that. So what's going to be the final account balance according to this formula if we plug in 12? Well, 1 plus 1 over 12, 12 raised to exponent 12. Okay, well it says 2.61. Oh, that's nice, isn't it? It's going up. But here's the thing, is that this is the Bank of Math 1326, and I'm willing to do any n that you want. This says every month. We can do it every week. We can do it every day. Every hour, that'd be fine too. Every second, every microsecond. That'd be fine too. Well, how many seconds are there in a year? That's an easy enough question with a calculator. So if we just pretend that there's exactly 365 days in the year, there's not, but we'll pretend, times 24 hours a day, whoops, times 3,600 seconds per hour. So if you look at that, that's thousands and then hundreds of thousands, 31 million. So there's 31 million seconds in a year. All right. What if we compound, that's 31 million. What if we compound 100 million times? That'd be, that'd be like 3 times a second. How high is it? The question is how high can we get it to go? Can we get it to go over $5? Can we get it to go over like 50? How high? How high can we get it? $100 million. Let's do it. Okay. So that's 1 plus 1 over, and then 1, 0, 0, 0, 0, 0, 0, 0, 0, and then raised to x1 at 1, 0, 0, 0, 0, 0, 0, 0, 0. Okay, there we go. There we go. So is it going to be like in the hundreds or in the millions? Yeah, that's right. 2.7, 1828, 1815 according to my calculator. But wait a minute. Do you recognize that number?
Yes, it's E.
So what I'm telling you is that the bank of Math 1326 has some interesting characteristics, but as it turns out, it is in fact not possible for your final account balance to ever exceed the natural number.
Actually, it's
Okay, so what I'm telling you is that this kind of idea is that we're taking the compound interest formula, which is discrete, where things were happening like every month or what have you, and now we've altered it to where we're saying, okay, we're not compounding every month, we're not compounding every week, every second, every microsecond. In fact, we're compounding in every instant. So when you consider that kind of model, it changes its name from discrete compounding to continuous compounding. Now, that being said, this is like an interesting concept to like explore, like in a mathematical sense, but I am not aware of any financial institution that offers continuously compounded interest. So it's sort of like a fantasy in that sense. So continuous compound interest. So in this case, like the other model, we have the principal, and it's denoted by P. We have the rate, which is denoted by R. We have the number of periods, denoted by T, and we also have the account balance, denoted by A. So notably, these are all of the parameters, and how many of them are there? 4, as opposed to the previous model that had 5. So which one is missing? What I mean is like which letter? N. The reason why n is missing is because this is the concept when you've said, well, we've let n go to infinity. So n's not part of it anymore. So there's no n. in this case, the model is A is equal to P multiplied by exponential RT. And for reasons I suspect are obvious, this is often referred to as the PERT formula. Okay? So, fine. But both of these models, they have a, you know, you can tell which one you're doing because if the question says compounded monthly or something like that, then that's the discrete one. If it says compounded continuously, then that means the continuous one. Okay? But they both have the fundamental property that they allow you to look at a financial situation through the lens of time. Which is to say that, you know, it's using these models, it's reasonable for you to talk about the value of money at different points in time. And given the interest parameters, you should have an expectation about which one of these should be bigger versus the other. So I won't do it, I won't take the time to do it because I want to get into some other things. But here's an example. You might, for example, have a niece or a nephew who's like just born, right? Or you know that they're going to be born, you know, like in a month or whatever. And you want to put some money down right now. You want to put some money down right now so that on the 18th birthday of this lovely nephew or niece, they'll have a sum of, say, $30,000. So the question is how much money would you have to deposit right now into an interest-bearing account so that the future value would be, what did I say? $30,000. So that's asking, what is the present value of $30,000 when that $30,000 is 18 years from now? So what I'm telling you is that you want this to be 18,000, and the question is how much is that worth right now? Does everybody get the idea? So it's two different amounts. It's the same money, but at two different points in time. Okay. That being said, here's a concept of a discrete money flow. This is also known as a paycheck. So you can imagine that you know, you've had a job or know what a job is at any rate, I'm sure. And you know, you get paid periodically. Like depending on your job, maybe you get paid monthly, maybe you get paid every 2 weeks. That's what I'm talking about. At discrete intervals, you receive a sum of money. This kind of arrangement is called a discrete money flow. Okay. Now that I only say that so that you can understand by way of contrast what I mean by this. A continuous money flow. So now, suppose that you have a job and that you receive money every 2 weeks. And suppose further, for the sake of argument, that you have direct deposit, which means that more or less your employer directly increases the balance in your bank account. If in the real world this occurs every 2 weeks. But in the calculus world, so we can talk about some interesting calculus stuff, we're imagining that actually this is happening continuously at every instant. So like you could sit there in real time, watch your bank account go up, you know, pennies, you know, click, 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 it's going up the whole time. And maybe at some times your bank account is going up, say, in the middle of the night. You know, maybe 1 or 2 pennies every second, because you know you're not doing much work there. But during your good work hours, where you're getting a lot of stuff done, maybe it's going up, 37 cents a second. I don't know. It's going up a lot. Okay, so then it's going up at different rates at different times of day. Okay. So given a money flow, f of t, what it is that you can think of this as dollars per time. So how fast money is coming in. The total money flow on the interval 0 to big T is, well, so if this represents how fast money is coming in, so what that means, this being lower here, is that you were making money, but you weren't making a lot of money. And then as time went on, the amount of money you were making per unit time was going up, and then it went down a little bit. So the question is what is the total amount of money that you made? Like if you were to just direct all of this into a single bank account, and then at the end of time t, you just wanted to look at the balance. What's the final balance? Well, it would be the integral of this, right? Because if you're making, if this is saying that, well, right here, if that's at a rate of, say, 17 pennies per second, and that's, 1,000 seconds, they just multiply it out, right? Little rectangles. Integral. So this is the total money flow. But here's the thing, is that you were receiving this money over a span of time. So you were receiving this money over a span of time, and then presumably because you just let it accumulate in the account, you weren't using it. So in that kind of way, you weren't being very wise with it, because if you have money that you're not using, then you need to cede control of it to someone else so they can use it so you can charge them interest. Which is to say that, if instead of putting this into under your mattress, or if you like, a zero interest bank account, what if we were putting this into a bank account or other instrument from which we could get interest? What if we were doing that? So here's a different question. This is, you could think of it like your employer is paying you, and the payout occurs over a course of time. Here's a different question. How much money would you be willing to receive right now as a lump sum instead of having this money flow? Alternatively, if you're familiar with the lottery, like the Texas lottery, the payout, there's two different payout options, right? There's the normal option, I guess, which is basically, it's still an outrageous amount of money. But when they say, oh, they won $75 million or whatever, okay, actually what happens is that you get paid something, like $35,000 a month for the next, I don't have any idea, like 100 months. Okay, that's what that really means. It's still an outrageous amount of money. Okay, but there's also something called the cash option, where you don't get paid every month. Rather, you just get some big lump sum that they just pay it out to you right then and there. And I promise you it's a lot less than 75 million. It's probably more on the order of like 10 million. Still a lot of money. So what I'm saying is that this is like the lottery payout that's happening every month. And I'm asking you, how much would you be willing to pay? How much would you be willing to receive right now in exchange for receiving this money the whole time. So do you get the question? How much money would you take right now? But here's the thing, is that we have to think of this problem carefully, because if this is, say, like 10 years, then the money that you get right here, that means that it is, and if you were to put it into an interest-bearing account, then it would accrue interest for 10 years, more or less. And then, you know, if it's been 2 years, then the money that you receive around here would accrue interest for about 8 years. The money that you receive about right here would accrue interest for 5 years. The money that you get right at the end wouldn't have, you know, any time to accrue any interest. What I'm telling you is that the amount of interest that each one could possibly be subject to depends on when you received it. So what we want to know is, how can we take all of this money that we received over a course of time and transport it all back to the beginning, to right now? To right now, because we need to decide how much money would I be willing to take right now to give up f of t. Okay. So, how much money would we agree to right now to give up f of t? So this idea, this is called the present value of a money flow. Okay, and just to remind you that you know, of where we were in the conversation, is that this is like the cash option on the lottery. Okay, so we're not going to have enough time to do it, but to get it done, because we're going to take a quiz. But I want to explain to you more or less the way we're going to do it, because there's enough time to explain it to you. So the way we'll do it is the same way we do everything, actually, is that we'll take this entire interval, and what we'll do is we'll construct an estimate. Is we'll take this function here, we'll take that function there, and then we'll cut it. We'll cut the time interval into 4 pieces. And what we'll do is we'll estimate that function with 4 rectangles, which is what we always do. And furthermore, what we'll estimate is we'll say, all right, in fact, what we'll say is that we received all of this payment, right? The entirety of this payment, we received it, say, I got to think about it here. Yeah, right here at the end. So this is like getting paid at the end of the month. So we received a payment exactly at that time, and then another payment exactly at that time, and another payment exactly at that time, and another payment exactly at that time. So that means that we want to pull, this is some future value, and it's at that time, and we want to pull it back to the present. So we'll pull it back to the present. Then this is a future value, and we're going to pull it back to the present. And that's a future value, and we pull it back to the present. And that's a future value, and we pull it back to the present. So we pull back 4 future values to the present, and we say, well, that's an estimate for the present value of this money flow by breaking the money flow into 4 pieces. But maybe that's not accurate enough. Maybe 4 pieces isn't going to be accurate enough for our purposes. Perhaps we could use more pieces. Okay, so let's use n pieces. So we break it up into n equal pieces, and we pull each piece back to the present time. And then that represents an estimate using n pieces. And then the calculus idea is that let's use infinitely many pieces. And that will tell us how we can calculate the exact value of the present value of a money flow by pulling all of the pieces from the future to the present. Okay, any questions before we have a quiz? And again, the whole idea here, and really to a large extent the purpose of going through this exercise, is to show you that there's like this one idea that we keep doing over and over and over again. And that is, we take an object, we carve it up into bits, we operate on those individual bits, we figure out the answer for all the individual bits, we add them all up, and then we let the number of bits go to infinity. It's the exact same thing over and over again. Good, let's have a quiz.